I'm Naresh Devineni. I'm an associate professor at City College of New York, part of the City University of New York system, CUNY system. I am teaching in the civil engineering department with my research focus on water resources management, hydrologic extremes, and stochastic methods.
What is a drought and why do we study droughts?
Drought is just a prolonged period of dryness, especially when it is really prolonged. That extended period is thought of as drought. Drought can also be thought of as a chronic shortage or lack of something expected or desired, right? That's just the conventional definition of shortage. Now, from a water resources standpoint, traditionally it has been conceived as a deficiency of rainfall or stream flow compared to long-term averages, or some indices have it compared to a specific evaporative demand. Now, these droughts can also be classified and have been classified into various categories. From a water standpoint, really the key features are looking at hydrology, looking at agriculture, looking at meteorology. So that's basically the idea of drought. Now, the reason we study droughts is sort of an obvious thing because it really leads to high economic and social impacts. Now, if you've been following NOAA and other news reports, what you'll find are the tangible financial costs that can be accounted for from an year-to-year basis, or you can also see this in the ongoing drought. But what we usually neglect are those hidden and latent costs, which are really the cost to the environment and the biodiversity. It's also important because it really affects diverse sectors, be it domestic water supply, be it agriculture water supply. A lot of industries also get reduced water allocations during drought, and it's really important for industrial water sectors. And its expression is also felt on a vast spatial scales and much longer time scales, and this is why it's important. We are seeing now in the Midwest that the entire Midwest is drying up with a lot of reservoirs going to their record lows, and it has been persistent, right? So you can see it's not just a time signal, but it's also a spatial signature, and that's why it is of much more importance for a water management context. It's really important to study droughts.
How has drought been studied till now, and what have been the limitations of those methods, especially in the modern context?
Now, generally, I think historically droughts have been studied by developing various indices. The classical definitions that we know from water resources management are these things called Palmer Drought Severity Index, Crop Moisture Index, Surface Water Supply Index, or even as simple as a standardized precipitation index. And these are generally commonly used for water resources management, agricultural drought monitoring and forecasting, and just like providing information, right? Now, a lot of us are also familiar with this portal called US Drought Monitor, which basically integrates all these indices into a central location. Now, these indices are typically based on it's measuring the deficiency of rainfall or stream flow or the weather conditions compared to its long-term average. So it's really, if you think of it, these are just supply-based. What is the water supply? Where is it coming from? How deficit is it compared to the long-term average? There are some indices. I think the Palmer Drought Severity Index certainly includes a general evaporative demand, so how much water evaporates from the region. And it also uses an overall water balance equation to come up with how much deficit you'll have. But it is an overall condition, just like a typical grass evaporative demand, but it is not specific to any crop. As if you're looking at a certain type of crop, corn versus wheat, their water demands are very different. So their evaporative demands are quite different, which means that the current methods are really not, for one, they're not pegged to the demands per se, but the index that already has demand in it is also not specific to for a certain crop within the agriculture, right? The main limitation is that, in the modern context, as demands are becoming more and more important, we have to start connecting water supply deficits with the changes in the demand conditions to understand droughts in a much more, in a better context. And that's what is lacking in the current measures. I can give you another example, just to make the point that demand really plays a major role, which may not be captured in the current measures, is that suppose you have two locations, Both of them have a very similar water supply signal, either it be rainfall or stream flow features or reservoir inflow features. But let's say one location has very high demand as opposed to another location which has a low demand. And then a drought happens, a deficit rainfall or stream flow happens. The region which has low demand may not actually feel the drought that much because the water demand in that place is not that much high. Whereas the region that has moderate to high demand, when there is supply deficit, this nonlinear interaction really becomes important, and that creates much more stressful situation because of the demand. Right? So that's why demand is really important, because that's the driving feature in terms of how much water is being used, who gets the water, how the water is being allocated, and things like that. And it's also useful to understand, once we talk about demand, it's also useful to understand which sectors are causing the main demands in those places. In some places, it could be agriculture demand, which is driving the major water requirement. In some places, it could be industrial water demand, which is driving. So droughts should also be understood from a sector-specific context.
How does the proposed index address this issue of linking demand to supply?
So, with those in mind, right? So what we started thinking was, can we derive an index, a drought index, which is really demand sensitive? And that's the essence of this paper, is that we came up with an index which is demand sensitive. Now, in this paper, we were showing things specific to agriculture, but it can be also done, as I mentioned before, that it can be derived for various demands, because the index itself, the methodology itself, is quite flexible. Now, what we also did is that this measure basically accumulates the difference in demand and supply in a given place. Demand can be current demand, today's demand, or demand can be historical demand. But really what it's trying to do is integrating supply and demand, which means that the deficit keeps on accumulating. So if there is an extended period of low supply and high demand, the deficit accumulates faster than if there are interspersed rainfall features in between that will alleviate the stress in those places. Right? So the measure that we actually derived is this integral called accumulated deficit. And from this accumulated deficit, we are now deriving many other important features, like how long the drought will be, how severe the drought will be, what is the recovery rate of the drought, and measures like resilience and relative recovery rates. Resilience defined by, if you're in a drought condition, how likely is it that you will recover from the drought, the fast recovery and all. And the recovery rate is how long does it take for you to recover relative to what drought duration you had, right? Those additional features beyond just I have an index sort of idea is really useful for water managers, as it provides plenty of planning tools in terms of looking at, if my region has a fast recovery but low resilience, what can I do to improve the resilience, right? So things like that can be now understood. And overall drought risk measures from a management context can be derived from all these drought indices. Now, what we also did is this a historical worst case scenario analysis based on historical drought, so that we have a baseline understanding of what droughts how droughts manifested and impacted in specific regions. And that analysis is also important, because if you're looking at future changes, then a historical baseline is quite important, because that sets up the tone for how the future climate will change and how we should manage the future climate relative to the future demands.
So using the proposed demand sensitive drought index, how does the situation look for Southeast US?
Now, this method that we derived, we actually implemented this at the county scale using daily water supply and daily demand derived from the agriculture. And then, it's applied at the county scale for the whole US. But if you look at the Southeast USA as a focus area, what we were finding is that the North and South Carolina areas have a low resilience, but the southern parts of Southeast, the Alabama and Georgia areas are having a relatively higher resilience features. It's interesting that even within a small area, we can see the stark distinction between some places having high resilience and some places having low resilience. And especially in the context of rain-fed agriculture, this is quite important, because it tells you what types of crops you can grow in the place. Now, At the same time, what we also found that all of the Southeast USA regions of the states have a relatively fast recovery rate, which implies that drought, once it hits the peak and it ends, so to speak, then its recovery is much rapid. And by recovery, what we mean is that drought has technically ended, and then you still have excess rainfall or excess water supply, which is now replenishing your system. So you need some time to recover completely to the normal state. And what we're finding is that in the Southeast USA, the recovery rates have been quite fast. It recovers. It takes less time to recover than it takes to creep to the worst drought condition. Right? While at the same time, some places have low resilience, meaning it may not quickly turn back, but once it turns back, it is much faster from there. Now, on a long-term analysis, what we also found is that when you look at historical analysis, we did like a statistical clustering method based on when the drought happened, looking at the worst drought in history, when the drought happened and how severe the drought is, and relative to the other important measures. And what we are finding is that, again, Southeast is divided into two clusters. If you look at the paper, you'll see this is cluster 1 and 3. This is to understand the worst drought scenario. Now, in cluster 1 region, or we can call it mostly Alabama and Georgia region, the worst drought relative to the historical demand, not today's demand, has occurred in the 1950s. And for the other regions, the North and South Carolina region, in the paper, we call it cluster 3. The worst drought occurred in the 1970s, again, relative to the historical agricultural patterns or agriculture water demand in that place. But what's also interesting is that currently, based on the historical baseline, the entire Southeast, the severities are generally less than 1, which indicates that, again, this is important for rain-fed context, is that regional rainfall would be sufficient in removing the water stress on an average year. Now, their relative recoveries are in the order of 0.6, which means that if I know how long the drought will be, then I will be able to tell you what is the average time it takes to recover fully from that drought situation, so that my soil moisture is replenished, my entire system is ready for the next cycle. Now, from a rain-fed context, this is quite important because currently the severity is less than 1 in most of the Southeast USA region. But in the future, if you anticipate climate to cause more and more droughts, or if you think that your demands are going up because you have more intensification of agriculture, which means you need supplemental water. So it might lead to moving this severity index into a value greater than 1, which indicates that regional rainfall may no longer be sufficient, and you may have to supplement it with irrigation, which is what they're already doing in the Southeast USA.
What is happening in the other parts of the United States?
Now, apart from Southeast, what is actually not mentioning in the other parts of the US is that some places, especially the Midwestern United States, the agriculture belt typically, and also in California, which is within California, the agriculture belt of California, where you're growing rice and almonds, the other water-intensive crops. Those places, what we identified are these are under chronic water stress, right? It's not like a general drought, but they also have this signal that shows that it has been chronically under water stress. Now, what that really means is that those places have their demands much higher compared to their average local water supply, meaning I have much more demand always compared to how much it rains in the place or how much general water supply I have in the place. So to alleviate that stress and on a chronic basis, what they are doing is that they have to depend on external water sources. This can be either groundwater irrigation, this can be surface water irrigation, or even just interbasin water transfers. Okay. Now, what this implies is that it's really putting stress, continued stress on the water supply systems to the point of running out of groundwater in some parts of the Midwest, like, you are completely running out of groundwater in places. Ogallala Aquifer is an example. There is also indication that you're really causing chronic water stress, which is really lowering your water tables, it's lowering your reservoirs, it's really putting extended stress on your water systems.
How can we use this demand-sensitive drought index for meeting the needs of water managers?
That's a good question. Now, the interesting thing with this index is that it's actually quite flexible. Now, when we did this, We derived it for one agriculture sector using daily timescale rainfall and evaporative crop demands, aggregated across all the major crops, major field crops in the US. Done it at the county scale because that's where the agriculture data is available. But because the index is quite flexible, it can actually be derived for any other demands that you're interested in. For example, I could have an index for domestic water supply. I could have a demand sensitive index for industrial water use. I could have one for agriculture. Even within agriculture, I can have it for what is the drought signal for corn, what is a drought signal for wheat, what is a drought signal for rice or cotton, any other crop that you have. If you know its evaporative demand, theoretical evaporative demand, we can actually derive this index based on the local water supply. If I'm managing a reservoir and I know my demands, I can come up with these indices so that I now clearly understand how much water each of the sectors need. Because really the index is how much additional water beyond rainfall that you would need that can be supplied either by the groundwater resource or from my reservoir system, right? So that's why it's very targeted to the use. It's also very targeted to the water managers. Now, this has been aggregated using a daily index, but if you're, and then accounting on an annual time scale. But if you're interested in looking at what is my seasonal water stress, seasonal drought, we can also derive the maximum seasonal accumulation of the drought. You can look at the maximum annual accumulation of the drought, or if you're interested in deriving the chronic water stress situation derived from the drought, you can look at extended periods, right? Over a span of 10 to 15 years, how has the drought increased and what is the stress that is causing on that location from a chronic standpoint, right? So you can use it for near-term operations, where I'll tell you what is the drought for the next cycle, next season, next 6 months. Or I can use it for long-term planning, because if I know my chronic water situation, I'm either looking at water conservation mechanisms, or I'm looking at enhancing water supply from various sources, right? For example, Florida does this. It works with both conservation measures of using, encouraging people to use less water, while it is also trying to go and develop new water resources based on groundwater extraction or desalination, things like that. Right? So it's a measure that can, if it is targeted to different sectors, you can now focus on how can I alleviate the stress. If you talk about the future climate, is another important thing, is that the index can actually be derived for what your future climate could be it using climate change projection runs or projected demand runs. So you can come up with what is your projected drought index for the future. The future can be a near-term six-month cycle, just looking at a seasonal forecasting context, or that future can be what would be my drought index, what would be my drought stress in the next 15 to 20 years, which could be a planning horizon for a water manager. So those things can also be derived in a nice, contextual way. Yeah, you're right. Yeah, I think once you know which demands are important, which sectors need the target, and then what my future climate would be, then I'm looking at how I can alleviate that stress by maybe I can derive some reservoir models and look at what percentage of water I can allocate to this sector depending on the stress of that sector, versus as opposed to just what they're currently doing, which is I am already over allocated or appropriated, and then I have to meet those standards. You can be very adaptive in terms of how you manage your water resources, because you're coming up with which sectors need more priority as opposed to the others. So one can also think of financial instruments that look at how you can tie up all these things into a drought insurance product. Also, some of the stuff that we've been working on looks at tying up these things with crop insurance. Thank you.